Good evening. I'm Milton Curry, Dean of the USC School of Architecture and the Della and Harry McDonald Dean's Chair in Architecture. Welcome to our spring lecture series. This evening's lecture, Thomas Auer, is supported by the Chase Leavitt Masters of Building Science Endowment, and Professor Doris Sung, Director of Undergraduate Programs, will moderate our Q&A session immediately following the lecture. Thomas Auer is Professor for Building Technology and Climate Responsive Design at the Technical University of Munich and a partner at Transolar, a very, really an extraordinary multidisciplinary firm that is certainly engineering and technology based, but really transdisciplinary in its work that extends from traditional buildings to arts installations, landscape, infrastructure, and transport systems. There's two very interesting buildings which I'm dying to see. One is not built yet, and one is built. The Art Gallery of Nova Scotia with the Transolar is doing with KPMG Architects in Toronto looks really fabulous. And the Fine Arts Library that Transolar collaborated with Wolfgang Chapelier looks extraordinary as well, and look forward to these and other projects that Thomas will talk to us about tonight. Thomas's work is has been distinguished by his work at Transolar and the work with several distinguished architects worldwide on award-winning projects that are characterized by innovative design and integral energy strategies. His research interests are in the field of climate-responsive building design, and the aim of his work is to optimize energy performance and environmental quality while taking into consideration local specifics such as the macro and microclimate and the influence of building form and material. The research focuses primarily on energy efficiency and how it influences the built environment, in particular with reference to building scale, form, material, technology, and district urban scale, urban form, infrastructure, etc. Simulation tools are used to assist in analyzing and optimizing the interdependence between buildings and their technical services. And Professor Auer studied process engineering at the University of Stuttgart. And since then, he's dealt extensively with issues relating to energy efficiency and user comfort of buildings within the framework of his role at Transolar. Between 2001 and 2008, he was a teaching assistant at Yale University. Subsequently, he held visiting teaching positions at the University of Kassel, École Spéciale d'Architecture in Paris, University of Sassari in Italy, and Ryerson University in Toronto, Canada. He's been a professor at TUM since 2014. I'm really looking forward to his lecture this evening. Please join me in welcoming Thomas Auer to USC Architecture.
Thank you very much for this nice introduction, kind introduction. Also, thank you very much for the invitation. I'm really excited and happy to provide this lecture today. Unfortunately, I'm not going to talk about the two projects you have mentioned, but I'm going to give you a little bit of an overview about the work at Transolar and current thinking about the transformation of our built environment towards, let's say, towards more a sustainable built environment and what that means. And I ask myself, are we lost in transformation? And that's certainly what driving us also in our research at the Technical University in Munich. So first of all, you already introduced Transolar. Transolar is focusing on, let's say, environmental quality and the environmental impact or the environmental performance of the built environment in indoors as well as outdoor environments. So these are our offices. And then this is my staff at the chair of the university. Most of them are in research. So about 80% of the people here are working in research. And I feel really privileged to be able to, let's say, work in the academic environment as well as being on projects with Transolar on, let's say, working on exciting projects. So I think there are synergies if being allowed to work on both fields. So that's the task. Our built environment has to become carbon neutral the European Union promised that we basically decarbonize the built environment, the building sector by 2050. This is a challenge, a huge challenge where we don't have real answers today, but we know that this is going to change, to transform our built environment. This is going to transform our cities. And not only, let's say, the decarbonization, also the climate adaptation. Our climate is changing. And so I hate to talk about climate catastrophe or things like this. I think it's not a catastrophe. A catastrophe, by definition, is something that happens all of a sudden. This is something we know exactly. I think there are pretty good models that predict the probability of what's going to happen. However, it requires a transformation and adaptation of our built environment. So the question is, can we design, can we, let's say, manage such a transformation and design it so that almost taking advantage of it? What do we do? At Transolar, we got invited to do an installation at the Architecture Biennale in 2010 in Venice. And we often call it climate engineering, what we are doing. And so when Sejima was the curator who invited us, when she asked us, we thought, what are we going to do? Because most of the things we deal with are the invisible qualities of space. That's how we call it. But people go to a biennale to see something. So we had this idea to do an indoor cloud, something we have done before. And the cloud is, for a cloud, you need to have 100% relative humidity. So if we have a layer of 30-ish degrees, let's say 80 Fahrenheit and 100% humidity, then this layer is saturated. And when it's saturated, you can spray in water, and the water particles, the droplets, do not evaporate because the air is already saturated. Now, warm, humid air has a lower density, is lighter than cold air. That's what we know. Cold air goes down, warm air goes up. So if we have a layer of cold and dry air below, this cloud layer is floating on it. But if the cloud layer is touching the ceiling, then we get condensation at the ceiling. So we need to have a lighter, a hot and dry layer above. So it's just this layering, which is the physics behind creating a cloud so that a cloud visually starts to appear. This is then how it looked like. Tetsuo Kondo, an architect from Japan, he designed the space. He designed the ramp where people could walk through the cloud and experience the different layers, the different climate conditions. And no, oh, here we are. And this was the cloud from above. So you see to what extent we can manipulate climate in, let's say, in a layer of a foot. Basically, we can create very different conditions in air. Now, this is not what we do in buildings, cloud specifically, but we recognize to what extent we can create comfort where people are and not conditioning whole spaces, or create a variation of comfort, create a dynamic environment. That's how we often call it, and not this kind of uniform conditions everywhere. This is what we see today, unfortunately. People put gadgets on something which is stupid to begin with. That's not how we can create a, let's say, a sustainable environment. That's certainly not a successful model. I think we have to be smarter, and we have to become efficient by design. We have to rethink design, and we have to rethink comfort and comfort standards. And comfort, talking about comfort and sustainability, we took this picture at one point from a magazine where they said, welcome to the breathtaking Tokyo Water Park, where you can wash away the pressure and stress of the overcrowded city. We found it funny, but let's say no matter how much energy they use in this facility, in this spa, the energy consumption per person is negligible. So we recognize that sustainability is not only about metrics such as kilowatt hour or carbon emissions per square foot. It's also about how many people use it. Do people really like it? What's the footprint per person using it? If we do a plus energy building or a zero carbon building, and nobody's using it, it's still a waste of resources. And so we can't disconnect this question of sustainability. We can't disconnect from environmental quality and from architectural quality. It has to be integral part of an architectural design. So let me show you this building where we worked with KPMB in the city of Winnipeg in Canada. It's for Manitoba Hydro, a utility company there. The building is already about 10 years now in operation, and it's quite interesting because Manitoba Hydro is still monitoring the building and publishing also some of the results. It's an 18-story tower on a 3-story podium, and it was supposed to be the most energy efficient high-rise building in North America. So this was the aspiration of Manitoba Hydro when we started to work on this project. We looked at the climate conditions of Winnipeg. We figured out that it's actually very cold with temperatures going down to minus 35 degrees. And at this point, the Fahrenheit and the Celsius scale, they meet. So it's about minus 30-ish Fahrenheit as well. And it's cold. They have freezing temperatures for almost half a year. They have 2 to 3 months with temperatures, let's say, around 0 Fahrenheit. And then in summer, they get 80, 90 degrees and fairly high humidity, much higher than Los Angeles. So it's a climate of extremes. The intermediate seasons, spring and fall, are pretty short. But then the conditions you see here with outside minus 35 degrees are very common. So when you talk to people, people always say it's cold, but whenever it's cold, it's always sunny. So it's this kind of dry cold where it's sunny outside. So we looked at how much solar radiation do we get in Winnipeg. And we figured out it's actually more than any location we have here in Germany. It's more than the city of Milan. It's almost as much as the city of Rome in Europe, and like comparing the numbers to Europe. And then we looked at how much do we get on a vertical south facade, because usually we measure solar radiation on a horizontal surface. But if we look at a vertical surface, vertical south, then in winter, when we have low sun angles, we have more sun exposure in winter. So we recognize that on a vertical south facade, we have more sun exposure, as I said, in wintertime than we have in summertime. So it was pretty clear that this is a good place to have to design for passive solar heat gains, like a passive solar design. And so we had an intense schematic design process where we worked intensively with KPMB, but also with everybody else involved. And we ended up with a scheme where with this 18-story tower on a 3-story podium, and in this section, we show how we operated in winter. So in winter, we get outside air into these winter gardens. So we have 3 6-story winter gardens stacked on top of each other. And we supply this air at 10 degrees into the winter garden, so that when the sun, 10 degrees is 50 Fahrenheit. Sorry, now I translate to Fahrenheit. We supply at 50 Fahrenheit so that when the sun comes out, the sun can further heat up the air before we supply it, utilize it into the building. And then we utilize it at about 70 degrees into the depth of the floor plate by a raised floor plenum. We have water features in these winter gardens to humidify the air. And then the exhaust air we take here into this chimney at the north part, down into the basement, where we have a heat recovery unit, bringing the heat by a hydronic loop back to the supply air into the winter garden. And then we have radiant tubing in the slab to provide heating and cooling. We have a geothermal system under the building with almost 300 boreholes going down 400 feet deep in a closed loop heat exchange in combination with a heat pump to make it very efficient. And then in summertime, as soon as we do not need heat recovery, we exhaust naturally by this solar chimney. And then we run cold water through our slabs to provide radiant cooling. We open up this south facade so that the winter garden basically becomes an outdoor terrace. This is the winter garden. This is the 6-story winter garden. This is basically the lung of the building. you can barely see, but this is the water feature on, let's say, on the back side of this picture, where water is dripping down mylar strips and in winter providing a certain level of humidification for the air before it's distributed into the building. And under these benches are the mechanical units integrated, which provide the air into the space. And then behind the panels on the left side, there are the units which take the air from this winter garden in order to distribute it into the space, into the office environment. So this is basically the mechanical room of the building. There are no mechanical rooms for housing air handling units in this building for office space other than the 3 winter gardens stacked on top of each other. And then to the east and to the west, we do have a double facade. The double facade has a couple of reasons. The main reason was that we get the shading device here outside the conditioned environment. So the shading device is in the cavity. And so therefore we deal with the solar heat gains in summer outside the conditioned spaces, but also people do have operable windows. So they are manually operated, whereas the outer windows are operated by the building management system to avoid overheating in the cavity. There was a question, I just got the question. It's the Manitoba Hydro building in Winnipeg with KPMG architects, just as a reminder. And then we have a displacement ventilation system, but about a third of the year time, we turn off mechanical ventilation and operate naturally by natural ventilation. So we have this adaptive system with this double facade, with the operable windows on the outside, on the inside, and the shading device in between, which allow us to really deal with the extreme conditions, particularly in combination with the winter garden as a buffer zone on the south side, so that we deal with these extreme conditions between winter and summer. And also from a building physics perspective, it was very beneficial to have this double facade, so that we deal with can really deal with the extremes and the cold bridges, etc. I don't want to go into the details, but this adaptability had many advantages in building operation, also in terms of environmental conditions, environmental quality, especially having the ability of natural ventilation in these extreme climate conditions, but also having everybody exposed to daylight. So what does this mean overall? MNECB was the energy code in Canada when we worked on this building. So this was the energy consumption maximum required, 258 kilowatt hours. These are average buildings in Canada. And then there was an incentive program when you are 20% better than MNECB. And this is what we predicted or projected in design. Our modeling showed that we are going to operate this building at plus minus 90 kilowatt hours per square meter and year. So this is the good news. The good news is that we have in this building, without conventional air conditioning, with this radiant heating and cooling system, we have half as many complaints for too hot or too cold compared to the other buildings Manitoba Hydro operates. And we have 1.25 less sick days. This is a very important number, let's say, particularly also if you look at money, at dollars. For 2,000 employees, 1.25 less sick days is something like $2 to $3 million per year. All the energy savings are around $1 million per year. So I'm not talking about productivity increase because people are in a more pleasant environment. Now with COVID, recirculation of air conditioning systems became a big point of discussion. We have a 100% outside air system in this building. People always appreciate the air quality in this building, but also everybody has daylight. Everybody can open the window for natural ventilation. So we are not talking about the increased productivity while people are at work. Only this hard number of sick days show us that it's an environment people obviously enjoy over, let's say, the more conventional and fully air-conditioned environment. Interesting was this question of complaints. Why do we get so many or significantly less complaints compared to a fully air-conditioned building, where you have a thermostat where you can say, I want to have now 72 degrees. In this building, the slab, the radiant cooling, is so slow reacting that if someone complains it's too hot, it takes at least a day to reduce the average temperature by about a degree or two. So it's super slow reacting. There are many reasons, but it's all speculation why we have such a good result. But the main reason is probably that in North America, people usually complain that it's too cold in summer. People take a sweater to work because it's too cold. And then the other question is, who is controlling the thermostat? So someone feels too warm where nobody felt uncomfortable. Nobody of the other people working in an open space office felt uncomfortable. Suddenly this air conditioner kicks in, you feel the draft, you hear the noise, and you start to complain. So this was the good news. Then talking about the bad news. So we looked at the energy consumption. We did a 2-year monitoring after final completion of the project. And we recognized that when the first year when we had full data was in September of 2010, the energy consumption was about twice of what we have predicted in design. And then looking at it in October, 1 year back, in November, 1 year back, we had some hydronic issues, which got fixed about a year after people, or more than a year after people moved into the building. You see here when that got fixed. But it took us 2 years until we reached the predicted numbers. That was kind of frustrating. And it was not like one big thing. It was not like, okay, the hydronic issue was the problem. It was like a million, or not a million, but a long list of small issues, like a sensor providing the wrong number, a motor broken to open the window or to operate the shading device, the control sequence here, a control sequence there. So all these little things you have to find in this kind of adaptive building structure, in this kind of adaptive approach. However, we showed that this is a model with this kind of adaptive systems, adaptive facades, where even in an extreme climate, we can do fully glazed buildings that provide good environmental quality and that are very energy efficient, very high performance. So here you see again a building, a picture from the north side with the solar chimney running the natural ventilation when we don't need heat recovery in wintertime. However, so what we recognized, again, it took us a while to get this building into a proper operation. And let's say the sad part here is that most buildings do not have a 2-year monitoring after final completion to find all these millions or thousands of small little issues. We did lots of those kind of buildings. Here you see just a few of them. And in the 90s and the early 2000 years, and still until today, we did lots of them, but we recognized it's not a robust system. It's a system that works even in extreme climate conditions. But obviously, if it takes us 2 years to get it to operation, it doesn't seem to be a robust system. And so this question of performance gap and robustness really started to drive us. And what's even worse, if we look at what gets built, all these glass towers, this is a picture from Dubai. Nobody is kind of trying to copy the idea of this kind of adaptability, of this kind of integrated design, integrated performance, integrated systems. Nobody, all these buildings are stupid. It's glass buildings in a desert. And not even in North America, almost nobody tried to copy us, copy what we did with Manitoba Hydro in North America, except for a few buildings, some of them designed supported by us, by Transolar, from our New York office. So that's the reality. So it's not a model which was successful. And therefore, I mean, that's my first hypothesis for today. We have to conclude that glass architecture failed as a model in terms of robustness and sustainability. It doesn't mean that Manitoba Hydro failed. No, the individual building is amazing. And there are many of these glass buildings that are amazing, but obviously it's not a model people try to copy. It's too complicated. Obviously, it's too complicated. So it's not a robust system and something we have to consider and think about. So this issue of performance gap also then started to, let's say, drive us, and we looked at it. We looked at it in more depth in research, and we found this study. We wondered, is this a problem only that occurred to us, or is it a common problem? And we found this study, which from the Royal Institute of British Architects, from RIBA, called Better Spaces for Learning, and they looked at almost 60,000 school buildings all over Europe. And they figured out that 95% of them did not perform as intended, 95%. So we started to recognize it's not the exception. It's actually quite usual that our buildings do not operate as designed. We build systems that do not work as designed. And we see significantly increased energy consumption, but we also see, let's say, issues with environmental quality, with thermal comfort, etc. Then we found this study in Germany done by the TU Braunschweig, where they say, first of all, naturally ventilated buildings have a 30% lower primary energy consumption compared to buildings with mechanical ventilation. This is something we always claimed. However, based on how we model buildings, you always get to the conclusion in our climate here in Europe that a mechanically ventilated building is more energy efficient. So the measured data show the opposite. But then the energy consumption for buildings in operation is in average 70% higher compared to the projected values. 70% performance gap in average. And the main problems are often building controls. So that's the realities. And then at my chair, we looked into a housing project. I'm going to jump over it. It was like 9 apartment blocks, affordable housing in Bavaria. And again, here you see from 5 buildings, we got data. Here you see always the difference between projected and measured data. 3 of them have no or negative performance gap. But as soon as we get more ambitious in design, those 2, there is almost 100% performance gap in operation. So this question of robustness and performance gap caused us to do a study, or 2 studies. Both of them got published, unfortunately, only in German in these 2 books. And the first book was about schools. So we started to look into school buildings, and we did measurements in 12 school buildings. And the first school building we looked at is the Theodor Fischer. Theodor Fischer was an important architect in southern Germany in the early 20th century. And here you see on the left side, this was a building of Theodor Fischer, which got completed in 1898. And then a school building from the modernism in the 20s. Then a couple of buildings from the 60s. Here, this is from Günter Behnisch, built in the 60s. Then a couple of buildings from the 70s, which got already renovated, 80s, 90s, and then some contemporary school buildings. And the last one is a timber school building, pretty brand new, opened in 2015, built out of massive timber. Florian Nager, a colleague at TUM with whom I did this book, or the 2 chairs did this together, this book. And it's a building he designed with his office and won lots of awards in terms of sustainability, and the Timber Award in Germany. So it was interesting to look at these different buildings, and then we did measurements, looked at environmental performance again, and took some pictures, always from the same position. You see right away the Theodor Fischer building from 1898 has taller ceilings, floor to ceiling space. So it's, let me translate into feet. It's 13, about 13 feet clear, floor to ceiling height. Whereas nowadays we do 10 feet, and it has 80 square meters, so 800 square foot, whereas nowadays we do 600. So the air volume per kid is about twice of a contemporary school. And then, so we did these kind of diagrams where we show measurements during occupation time. And you see here the outside temperature on the horizontal axis, on the vertical axis, the indoor temperature. Each dot represents 5 minute measurement. And then the two lines indicating the comfort zone. So don't want to go through all the numbers, but was interesting to see that among all buildings without mechanical cooling, the Theodor Fischer School from 1898 performed the best, provided the best thermal comfort in summer, unlike we had systems for mechanical cooling. In terms of air quality for all school buildings without mechanical ventilation, having only natural ventilation, so this showing CO2, the Theodor Fischer School from 1898 had the best air quality. These are the mechanical rooms. So the Theodor Fischer School has a boiler room with about 300 square feet, whereas nowadays, if you look at the bottom right, like here, the Diedorf School, there's a gym basically built under the building to house all the mechanical units for providing high efficient systems, sustainability, good air quality, and so on. It took them 3 years to get the system to operate properly. They do have occupancy sensors and CO2 controls in every single classroom, managing a variable air volume system, we call it VAV, which started to become really complex. And so this is the Theodor Fischer School. You see the windows go up and become very tall. And then what we also recognized, we also measured the acoustics, reverberation time. And there are no measurements, no measures to improve, no acoustical absorption in those spaces. But due to the height of the space and the fabric required as a curtain, we had a really good acoustical performance. We had a really good daylight performance because those windows are so tall, providing daylight deep into the space. We had really good thermal comfort in summer because we do have this very thick, like 60 centimeter thick brick walls, and the internal walls are 40 centimeters, so almost 1.5, and the outer exterior wall 2 feet thick brick wall. We do have the best air quality for all naturally ventilated buildings because it's more volume per kid. So it's ridiculous. This is a really robust system of a building which is 120 years old, which in 120 years did not go through a major renovation. There was no major renovation in 120 years. Of course, it's listed as a heritage structure, but today we would call it multi-objective optimization. But in a very holistic way, the building performs really good. And even we did a comparison in energy, even the energy consumption is only 30% worse than the Diedorf building of Florian Nagler, which is super high performance, state of the art in technology. So this is a view onto the building. So this is kind of frustrating. So we started to think about what happened in 120 years. And not that we believe we should, again, design buildings like this. It doesn't even need an external shading device. The thermal mass is so much that they can deal with the solar heat gains with, let's say, without external shading device, just using the curtains on the inside. So the embodied, there was a question about the embodied carbon. I'm gonna come to this a little later. So this is this question of robustness. Then again, we started to dig into, and we looked into. There's actually a tool or a methodology we can use for robust optimization. I don't want to go into the details, but the beauty of it, we always talk about high tech and low tech, adaptability, etc., etc. But what is this? This is all gut feeling, more or less. But robust optimization is a methodology coming from mathematics we can use with our modeling tools in order to describe how robust a system is. And then we started this Build Simple project. In German, we call it Einfach bauen, Build Simple, with Florian Nagler, a research project at the university. And I said, like, we have to reduce complexity in building design. We have to create a more robust model. And so we started, this is done by Florian Nagler, his chair, rethinking what layers do we need. And so this is, the left is a section of a concrete building and how we would usually build it in Germany, with external shading devices, with insulation on the outside, with a floating slab for noise insulation, for noise disconnection of spaces. And we said, like, can't we get from here to here? Get rid of all these layers, coming back to a monolithic wall where we use just one material, no composites. And we studied this for concrete, for insulating concrete, for wood, as well as for brick. And then we did modeling and looked at, can we kind of prove, Theodor Fischer, can we rethink also spatial height? Because of economical pressure over the last 100 years, we always decreased height of spaces. And we said, like, what's the ideal space configuration? And so we looked at 81 geometries for orientation, 3 different building materials I mentioned, 3 different types of glass. So we ended up with 4,000 options. We studied and did modeling and tried to find a solution. And then also looking at uncertain boundary conditions, on how these uncertain boundary conditions then can influence the result. So this is basically something we use to test how robust the system is going to be. And then we did life cycle studies, and we figured out, we designed this as towards the minimum energy standards we have in Germany. So no extra standard. So no passive house, no nearly zero energy building, how we call it today. But then if we look at the life cycle of 100 years, then we recognize that even the brick building, we put in some uncertainties here, and how people operate temperature and ventilation, natural ventilation. But in the average case here, even the brick building, we are still as good as the nearly zero energy building, which is basically a passive house, when we look at it over a period of 100 years. The wooden building is even much better. And then we found a investor, the B&O Group, who built 3 of these buildings, and Florian Nagler designed it. And so this were the result. And suddenly, so there's now a lot of discussion, debate in Germany about these 3 buildings. There was a whole page in a big newspaper talking about those 3 little buildings, which was kind of funny. However, what you see here on the left side, this is the concrete building. So it's monolithic insulating concrete. The middle one is the timber building. The right one is the brick building. You see the shape of the windows. This is because in the concrete building, there is no steel, no reinforcement. We said no composites, so concrete only. And if there is no steel beam inside, you can't have a horizontal window. So that's why you see this kind of arch type windows, whereas in the timber building, you can have a beam. And also in the brick building, so no beam, it's brick in this arch type masonry wall, creating this shape of this window. We took out all the layers, we minimized fenestration ratio, we increased spatial height so that with smaller windows, we get light deeper into the space. so that we don't need external shading device in terms of summer comfort, thermal comfort, overheating in summer. So everything we learned basically from Theodor Fischer, we try to apply here to really minimize complexity. But we accepted on day one a higher energy consumption. And so as a next step now, we are translating this in student housing. So we have these 3 projects under design, same idea again, the 3 different materials. And here you see we extended the roof, cantilevering the roof. So because the roof is fully covered with photovoltaic to take care so that we get towards zero energy in these buildings, even though we accept a higher energy consumption on passive or demand for heating in particular. And so this is a picture into the model you see on the left side, and the space, and then into one space on the right side. And the space becomes this tall. So again, here we are talking about something like 12 feet, so that there is a bed on top of the bathroom. And therefore we could even reduce the depth of the building, making it more efficient. So it's this play also, again, with spatial height in order to provide quality. I'm gonna jump over this, or maybe just quickly. Okay, we have fat walls. Now the question is, what does it mean in terms of embodied energy? And when we look at 1 square meter of wall, so 10 square foot of wall, and we look at the global warming potential and compare different wall assemblies, then you see here a double facade, a floor to ceiling, a fully glazed double facade, how much embodied energy we put into such a facade. And then if we look at concrete with styrofoam insulation, then we are here. If we look at brick, sorry that it's written in German, if we look at brick, we are about half of the glass facade. If we use rammed earth in combination with timber insulation, so mineral wool coming from wood as for insulation, then we can even become negative. So what I want to say here with this little diagram, looking only at cradle to gate, the thickness of a wall is not necessarily, let's say, has a relation to the embodied carbon. It very much depends on what kind of material we use. And this is something which is now the hypothesis too, is that massive buildings are per se more robust. However, this doesn't necessarily lead to more embodied carbon. And I want to finish with an example to illustrate what I mean. It's the Alnatura Arbeitswelt in Darmstadt, designed by Haskuk Zemmerich architects here from Stuttgart, where we used rammed earth for this wall construction, also for, let's say, control climate not only in terms of temperature, but also control climate in terms of humidity, because rammed earth has really good properties in terms of humidity control. There's a company in Austria called Lehmton Erde, Martin Rauch. He developed a process how to industrialize the manufacturing of these rammed earth walls. And in order to deal with cold, there is a layer of insulation. You see in the middle, it's foam glass. So it's also a mineral material we put inside the rammed earth wall. And then during construction, he prefabricated at the site. So he built up, he rented a warehouse and built up a tent here for drying out these prefabricated wall assemblies. And you see here, there's also piping integrated we use for radiant heating and cooling on the inside. And here you see when it's installed, so then with a cherry picker, he brought these walls, let's say these prefab walls, onto the site. Here again, you see the piping on the inside for heating and cooling purposes. So this is the insulation layer. And then this is how it finally looks like. We still have a concrete ceiling, a concrete slab. I think that's the next thing we have to think about, how we can get rid of concrete slabs. We did measurements. I don't want to go into the details. We measured this building over a course of a year now. We again have some issues with the controls, but we see a much more robust behavior, and we see that the humidity control works really well. Again, picture, we have an atrium in order to provide daylight into the depth of the floor plate. The client, Alnatura, is a supermarket chain for organic food. And it's the headquarter for 500 people. They decided that they want to keep this as an open space, so the whole building is basically one room. We looked at embodied carbon. I'm gonna jump over it. What we recognized is rammed earth has a really low embodied carbon if it comes from the site. So we did another building with rammed earth, same technology with Herzog Demeron in Switzerland for Ricola. There we got the material from the site. Here the material got transported from outside. And we recognized that this transportation is killing the carbon balance of the material. But this was, let's say, a research project. Then we followed up with the Technical University, where we really monitored each truck that transported the material on site. But anyway, so we see, let me conclude, we see that robustness is a methodology we can use in building design. We recognize that these buildings, these highly adaptive buildings, have issues in terms of robustness, have issues in terms of performance gap with the controls. We see that the world builds stupid glass buildings and they don't copy the model. So we have to be smarter. We have to come up with a model that is more robust. And let's say if we get to, that doesn't mean that we can't do glass buildings. That's not what I want to say. Of course, we can still do glass buildings, but we have to build smart glass buildings, not stupid glass buildings. But as a model, I think we need to think in a different way. We need to think very holistic. And this question of robustness really helps us to better understand the holistic performance, environmental performance of buildings and our built environment. Thank you very much.
Thank you very much, Tomas. That was actually an amazing, excellent lecture. Very much enjoyed it. We will be having an opening up for questions now. If everybody can post questions in the Q&A button below on the bottom of your screen, that would be great. And we could proceed with some questions. What I'll do is, I guess I'll start out with some questions. I have many of them. And the projects are amazing, fabulous. They cover a lot of ground. And then as the questions start coming in, maybe we can start addressing some of those as well. I have a question about this idea. Again, you talked about this robustness, that we need to design things that are more robust in order for them to potentially even be copied. And you talk about the Manitoba building and the question, why aren't more people or more buildings going up that are like that are being copied? But besides just designing things that are more robust, what would you say are some of the hindrances or the hurdles that we have to get past in order for those things to change so that buildings can be designed and built more smartly? Would you say that it's more of a policy issue or a cost issue that's preventing more people, more developers, more designers from looking at that?
I mean, when you look at the Manitoba Hydro building, we're working on, let's say, with many architects in North America, many competitions. And whenever there's a certain aspiration, if it's an office building, if there's a certain aspiration on sustainability, one of the precedents we look at, or people look at, is always the Manitoba Hydro building. Now, so it's not that people don't know this building. So your question is absolutely legitimate. So why is it not copied? I think one of the issues is people are risk averse. Let's say they still consider it a risk having a building with retractable shading device. In North America, people are also paranoid about maintenance. So what does it mean to have all these motors that operate these shading devices? operable windows, and then people can interfere, people can open their windows. So what does it mean? And there's this this, yeah, how can I say, this philosophy that coming from mechanical engineers, I'm a mechanical engineer too, I mean, I can say that, but mechanical engineers, they have the desire that they want to keep a space under control. They want to control temperature, humidity. They also want to control the pressure in a building. And this disappears or fails when people open the window.
Mm-hmm.
But if we have a robust system, you don't need to control. I mean, that's the whole idea also of the Manitoba Hydro building, that the building, this, let's say the passive systems, should be able to control the space over a long period of time. And mechanical systems are only supplemental. But this is not a mindset which somehow arrived in design. That mechanical systems are only supplemental. Of course, we can have extreme conditions, like at minus 35 degrees in Winnipeg. You need a heating system,
Mm-hmm.
and you need to have mechanical air supply. You can't open a window at minus 35 degrees. But to consider it supplemental is not something people are used to. And then developers, I mean, as long as they can, as long as they find tenant, why should they change the model? So I think we can only change the model either by regulations. This is difficult. This is then something we also struggle with. It would be better if tenants and people desire it. If people say, we don't accept these bad spaces anymore with no daylight, with draft, with noise, with recirculating air. Like think of COVID, we recirculate air in buildings for heating and cooling purposes. This is stupid. I think we have to do, people have deserved better. Now, I think it's up to us to come up with a model than people, which might be less expensive. I don't know, less operable parts, less movable parts, so that people start to copy it more. I think it's up to us. It's a task also for research to find, and I think you are working on interesting systems in terms of adaptability, which don't need motors to operate, which are self-controlled, no controls, all these issues we have in buildings. If you get over this with smarter systems, that's what we need. And this is, let's say, an important task for research as well.
Yeah, oh, definitely, definitely. I have another question too. I think it covers something else that someone else was asking. And you seem to be able to do a lot of this post-occupancy measuring and testing. Who covers that? Does the developer? Is it done through the university? Who pays for those types of testing and measurements?
I mean, the school buildings, there was a research grant by public funding. Manitoba Hydro was paid by Manitoba Hydro. Like if we do it in a Transolar project, also the Alnatura project, it's paid by the client, but it's difficult to convince. People believe, clients believe that after final completion, a building works. It's like you buy a car. You go to a car dealer and you expect that you drive from the car dealer and the car works. Unfortunately, that's not the case for a building. I mean, that's the truth, that what we recognize. It takes, each building is unique, particularly the controls are unique. It takes time for buildings to really work as designed, and it's hard to convince clients, but every once in a while we are successful.
Yeah, keep doing it. Okay, so we do have a few questions here. I'm going to start with one from Denise Curry. How best to invest in new ventilation systems for schools as they prepare to return to in-person instruction during COVID-19 pandemic? This is always the question, right?
Yeah. We have many debates about ventilation in schools in Germany as well. And what we recognize, the best we can do is natural ventilation. There's no mechanical systems which works better, and even, or let's say, people doing research with this pandemic and the COVID came to the conclusion: open your window. People complain about draft, of course, but that's the best we can do. Let's say to have a routine how to open the window. And I promote this at Transolar as well. We have a naturally ventilated office here in Stuttgart. I'm not successful yet, but not many people are at the most people are in home office right now anyway. But you can't work for 10 hours a day being fully concentrated. So I always suggest let's work for 25 minutes, highly concentrated. It's silent, no phone calls. If someone has to take a phone call, he has to leave the space. So totally quiet. And then we open the window, and then we have another 25 minutes where we chat, where we have phone calls, etc. And then again, having this concept. So I think it would be interesting to kind of integrate these ventilation routines into our working routine. So this is what I promote. Again, I haven't been successful yet, but I continue to use the office as a guinea pig.
I like that. I like that. Maybe you can just walk around and open the windows every 25 minutes
Yeah.
and tell everyone to shut down or shut down the internet maybe.
Yeah.
Okay, so we have more questions here. I will just keep going down the list here. Along those lines too, a little further. Given school shootings, what changes would you suggest to create safer designed classrooms? It's a tough one, huh? Maybe that's out of the HVAC mechanical engineering category.
Yeah, indeed. I never thought about this. I don't know.
Okay, so we'll keep going here.
I
From
think
Mark Schiller.
sorry,
go ahead.
we have to get rid of guns. I mean, that's probably
That would be one way.
Yeah.
Mark Schiller. The comparisons of embodied energy are very interesting, especially carbon sequestration in wood. How does that compare with the operational energy over the lifetime?
The operational energy over lifetime is always more carbon. However, I think we need to see two things. First of all, the availability of resources. The building sector uses the most resources worldwide. Cement production is responsible for 8% of the carbon emissions worldwide. This is insane. Sand, we run out of sand. So despite this carbon calculation about the lifetime of a building, where operational energy is more dominant, I think we run into other issues of resources. So that material resources become the main question of the next decades. The other thing is operational energy, carbon emissions from operational energy is going down. Like in Germany now, we increased our renewable power generation to almost 50% over the last 15 years, and it's going to go up further. So the carbon emissions from operational energy will decrease over time, but we invest into carbon from materials now when you do the construction, and you have to offset it to become carbon neutral. And then that's the next thing. We look at it over a lifetime of 50 or 100 years. But if we want to become carbon neutral, if the building sector completely has to become carbon neutral by 2050, everything we build today, we have to offset the carbon invest in 25 years by 2050. So making a long story short, yes, right now, the way we model it, operational energy, carbon emissions from operation is dominating. This is going to change very quickly. So the main focus now should be on material use.
Yeah, definitely. We've got a lot of work to do in that area.
Yeah.
Couple more questions actually from Mark Schiller and more to follow. In comparing the old school building with the modern schools, did you even get to the fact that the modern schools were requiring additional embodied energy, whereas the old building is embodied energy that is already spent?
I'm not sure if I get it, but the embodied energy, let's say, usually the way we model it, I mean, it's always, let's say, you have rules how to model it. We consider 50 years as a time period for the embodied energy of, or the embodied carbon of the material. So if it's after 50 years lifetime, the embodied carbon is 0. That's how we model it. So how how about 120 years? I don't know, minus minus something. It's just, let's say, the way we balance it. But anyway, if a building stays there for 100 years or longer, it doesn't matter anymore how much carbon we have spent. That's something we always have to bear in mind.
Right, it doesn't just keep continuing, I guess, over time.
Yeah.
Another question, on the west facade of the MHP building, you have a double envelope. Wonderful. Does the cavity vent hot air from the top, or do you rely on the outer vents spread across the facade?
We rely on the outer vents. So the idea is that the inner windows are closed in summertime. The cavity heats up. I mean, that's what happens on a double facade. The cavity gets hot in summer, and we dissipate the heat to the outside by the outer vents, which are motorized and controlled by the BMS. So that's the idea. And in that period, when it's really hot outside, people should keep the windows closed, and we operate the building on mechanical ventilation.
So on that building, just an added question, is everything automated, or can people actually override the system? And will that throw off the performance of the building itself?
I mean, there's not much people can control, or there's not much to control anyway, but people can override the shading device. People can open, the inner window is not motorized. So people open it manually. We had a long debate of how we control natural ventilation, because we literally completely turn off mechanical ventilation, and they monitored it about a third of the year. There's no mechanical ventilation in that building. And the solution was then very simple. They have an intranet, and people get a notice by their intranet saying building is in natural ventilation mode. And then it's the responsibility of the people to open the window. If they don't open the window, they don't get fresh air. Like at home, nothing different, and nobody died yet. The opposite is the case. We have less sick days.
Yeah, people are getting less sick. That's great. Another question from Lucy Liu. Since Los Angeles is a very sunny place, how do you think the strategy would be different? Is a similar multi-level space going to work for ventilation and heat moderation?
I mean, of course, you could do a similar approach. Let's say this kind of double facade adaptive system allows very well to really adapt to different conditions, also to very sunny conditions. However, Los Angeles climate, you wonder, like most of the year, do you even need a facade? Most of the year, a roof would be sufficient. So it's so moderate. The Los Angeles, I mean, the closer you get to the coast, the better. Greg Lynn once said to me, living in Venice, he doesn't need any heating nor cooling in his building. In summer, he just opens the window, and in winter, if it gets too cold, he keeps the lights on. That's sufficient. No, so that, of course, if you get more towards downtown, it's a little different. However, it cools down at nighttime with a little bit of thermal mass, a little bit of natural ventilation. I mean, do you need this really complicated double facade system in a climate like Los Angeles? No, I think you need good shading. And since it's always sunny, basically, it's always, you can even think about having fixed shading. Do you need to have this adaptability? Of course, it's always good in terms of daylight, in particular, when you don't have sun exposure, direct sun exposure on a facade, that you maximize daylight and not having a fixed shading in front of your facade. But however, I think Los Angeles is really a very forgiving climate where you can do really nice, robust buildings. The biggest stupidity I always found in North America, also in places like Los Angeles, that the floor plates are so deep that people are so disconnected from the facade, which is where you have access to these really beautiful conditions. If it's not a wildfire, I've just recognized now working on a project on the West Coast that wildfires, air quality during forest fires becomes a big question. However, that's a short period of the year. Other than that, you should give people access to the facade.
So you would actually think that in Los Angeles, we would have more robust buildings here, but
Yeah,
surprisingly, we don't. And if you think also, given what you're saying, we would actually put a little more into the material development because we don't have to worry about extreme climates as much as other places.
yeah,
But maybe that's something that we really have to think about for our local area.
yeah.
Another question from Olivier Touraine. Thank you for a great and late lecture. For you, it is early in the
Indeed.
morning, I think, because Tomas, I think everybody knows that you're in Germany. Do you see differences in terms of typologies of projects between your New York City, Paris, or German offices? More adaptive reuse or new buildings? Like your different offices, what do they have a specialty in what they're doing, or is it a regional thing that they just happen to be working on?
No, I wouldn't say that. What we recognized over the last couple of years, and particularly here in Europe, but also in North America, since the Fridays for Future protesting, that people take it more serious. Also developers, like developers come to us and say, we have to change. So they are also getting concerns about the value of their building in 10 or 20 years if they keep it in their stock. So this has changed. This is what we see as a change. We also see that we have more serious debates about keeping buildings and not just tearing them down. So this carbon investment into a superstructure, which is there already, is part of the debate in our projects. However, I don't know to what extent we are representative for these kind of questions, because like we get asked by people or for projects where there is a certain level of aspiration, so and a certain level of openness. So I'm always a little uncertain if we are really representative, if we have a representative view on things.
So we just need more climate engineering firms like yours then, like Transolar.
Yeah.
Okay, another question from Andrea Mauk. Sorry if I'm mispronouncing it. What can we do for ventilation in extreme climates such as the desert?
Oh, yeah, good question. We are working right now in Saudi Arabia, and we did some work in Middle East. We also promote natural ventilation there. Sand is an issue because you always have sand in the air. It's not a health issue. You have to clean a little more often your space because you get all the sand into it. We did a nice school building in Damascus. I mean, the beauty there, which is purely natural ventilated, no air conditioning. They have 100 Fahrenheit outside in summer every day, but it cools down. That's the beauty of a desert climate. It cools down at nighttime. It's a dry climate. It's not a humid climate like Singapore or so. It's a very dry climate. And so from a climate perspective, such a desert climate is beautiful for natural ventilation. You need to think about how you pre-cool so that you do not get 100-degree air into your building, how you pre-cool it. In the Damascus building, we have ducts in the slab, in the ground slab. We use this to pre-cool the fresh air so that it enters at 80-ish degrees. And without any air conditioning, we maintain temperatures of maximum something like 85 inside, so that it was actually the parents then who said that at hundreds degrees outside 85 is beautiful, is good, and it is more healthy. And we do now have the adaptive comfort standards where we can prove that people appreciate this environment in a naturally ventilated building. So it's the sand you have to deal with, but if you kind of not just having an operable windows, if you have like chimneys where you redirect air, etc., there are ways to minimize the transportation of air that gets into the space, of sand that gets into the space.
Sand. Interesting. Okay. Another question from Mark Schiller. Although natural ventilation is outstanding for COVID separation, is there an opportunity in recirculating systems using UV to sterilize the air?
I'm not an expert in this. They claim it. They claim it. Yeah, it seems to be a possibility to clean the air. We're just working on a research grant to test it in a space. What I find more interesting than to have decentralized units, it's supported by let's say by kind of a restaurant association in Germany. They want to have, let's say, safe places. They say COVID will go, but it will stay in people's mindset. And what they question is, can we have decentralized systems that communicate to each other so that we are sure that a group of people sitting at one table is not affected by another group of people somewhere else? And this is something in the way we mechanically ventilate spaces, we can't guarantee, because we always assume that we mix a space. We want to always intend to have an ideal mixing. And so all these aerosols, we always keep in the space at a certain level of concentration. So it's not only, let's say, the recirculation where we bring things back. It's also the way how we utilize air into the space and how we operate the space itself, which we need to rethink. And that's the beauty of natural ventilation. When we open a window, we displace the air. We don't mix it. Natural ventilation tends to displace the air more than mixing. So that's why it works really well now with COVID.
Another question from Mohammed Al-Wataid. Sorry again. Do the rammed earth walls contain cement? If yes, what is the percentage? Also, what are the average temperature and humidity differences between indoor and outdoor in the project that adapts rammed earth walls? And then a follow-up question is, where has that been published?
It's okay. One question after the other. Yeah. So first of all, zero cement, no cement. Lehmton Erde, the company from Austria, who also did the Herzog-Demeron building in Switzerland, they claim that we never measured it, we never tested it, but they claim that as soon as you add cement, the humidity transportation is killed. So this humidity control is immediately killed. Again, I have no scientific proof for it. But so that's the reason, one of the reasons why they do not add cement. So it's pure rammed earth, 100% rammed earth, this wall. And in Darmstadt, in this building for Alnatura, as I showed, we added a layer of insulation so that we follow code requirements in terms of U value of this wall. But then we can deal with normal indoor temperatures of 70 degrees and having down to something like 0-10 Fahrenheit outside in winter time, in extreme winter. The Ricola building has no insulation. It's only massive rammed earth. But there they don't need, it's a stack storage building for herbs. There they need humidity control, but no temperature control. So the temperature in winter goes down to something like 10-ish degrees Fahrenheit. And therefore the building doesn't need any insulation.
Okay. Maybe just two more questions. I know you're very tired, Tomas. From Kyle Konis, in the US, ventilation standards, ASHRAE, are focused on promoting mechanical ventilation as the means to provide minimum ventilation. Are standards in Europe headed in the same direction, or is an alternative path being taken?
No, I think the standards are very similar in terms of minimum ventilation rates in Europe and in North America and ASHRAE. There's not much of a difference. What we recognized is that with all these, let's say, natural ventilation approach, like with Benish, we did in Portland a building for PSU with natural ventilation. Let's say even in North America with the North American standards, ASHRAE 55 has the adaptive comfort standards. ASHRAE doesn't give us any limitation to do a fully passive building design. It's the interpretation of ASHRAE where we always come to the discussion. It's a that we need to keep spaces under control, etc., etc. But literally, like ASHRAE was never a real issue like there's everything is in ASHRAE. It's actually in terms of thermal comfort, it's even more progressive than the European codes.
Okay. And here's the last question. I think this is very good for our students in general. Rather than relying on smart buildings with finicky and costly control systems, I continue to educate myself on dumb building technologies that provide mass durability and diurnal heat transfer. I guess in some ways, what Christian Arndt, who asked the question, is considering smart and dumb can also be transposed, right? Because maybe the smart one is actually what, Tomas, I think you're suggesting in your lecture is the simple answer. Can you recommend resources for my education?
So now it's good. Resources. Daniel Barber did a really nice book on, let's say, vernacular architecture and climate control in vernacular architecture. I think this is really good. But I think what you said is indeed true. Smart, we always consider like a smartphone or something controlling a system, controlling a space. But why should it be smarter than people? Why should a smartphone or building controls know better than people what they want and what they desire? And this is what we recognized also in air quality. We did in the school building questionnaires, surveys of how people perceive air quality. And there was no correlation between what we objectively measured and what people subjectively perceive. So why don't we rely more on people sensoric and what people desire than always trying to dictate in this, what we call smart buildings? I think people are smart enough to know what they need and what they want.
Yeah, it really questions the terminology and how we've come to use the word smart too.
Yeah.
But thank you very much, Tomas. Thank you for a wonderful lecture. Very educational, very informative, very inspirational.
Thank you very much.
I hope we didn't keep you up too late.
It's fine.
I know it's early morning for you right now, but I think I'll leave it to Milton to close the session. Thank you.
Thanks, Doris.
Thank you, Doris, and thank you, Tomas, for just a wonderful lecture and, as Doris said, an inspiring send-off in terms of the conversation about technology and our climate and how architects are responding in so many different ways. So I think it's great to see the work, and it's unfortunate in a way we're on Zoom for you at 3 a.m. But as soon as it's possible, we'd love to have you come to LA and interact with our students on many of the issues that you talked about. So thank you.
Thank you, Milton. Thank you very much.
Thanks, everybody. Good night.